Welcome to this mini lecture on AC circuits. This video will include a discussion on alternating current, its relationship to direct current, and some applications of AC circuits. So AC/DC is not only a standout band from the 1970s and the Pride of Australia, but it stands for alternating current and direct current. So that's actually what AC/DC means in the name of the band, also known as Akadaka uh, by Australians. But the story of how they got their name was um, one of their sisters saw the AC/DC symbol on a sewing machine, and the band felt that the name symbolized, their raw energy and power-driven performances. So alternating current and direct current differ in the sense that alternating current changes polarity over time, and direct current maintains a constant direction or polarity over time. And you can see the symbols here for direct current and alternating current. Okay, so just as a reminder for your signals and systems knowledge, that alternating current can come in several different waveforms. The most common one is a sinusoidal waveform. And the AC that's in most homes and offices have that oscillating voltage that produces a sine wave. And so again, for your signals and systems future classes, if you take any, we look at the number of times an alternating current repeats a full cycle. That's called the frequency. And the maximum direction is called amplitude. So in either direction, either positive or negative, that maximum that the sine wave reaches is called amplitude. So what's actually happening here? You can see the portion of a sine wave. The amplitude starts at a given value and then reverses polarity and returns to an initial value. And so that's what one cycle is. So again, you can see here, you start at any amplitude, whether it's 0, the maximum, return to that same amplitude, and there you get one wave cycle. So the rate at which the voltage and current changes, polarity can be quantified as cycles per seconds. So this is usually expressed as using the unit hertz. So if you see Hz. So in the United States, like I said, our electrical power is distributed as a sinusoidal voltage, and it completes about 60 cycles every second. So that's about 60, it has a frequency of 60 hertz per second. So you can see here the alternating voltage and current. All right, so like I said, the wall outlets use alternating current, which is what we've been looking at here. But what you've been studying in your previous circuit analysis, we looked more at direct current. So direct current is usually what batteries use, and a lot of your appliances use DC as well. So I have a little exercise for you guys if you want to get, either your laptop charger or really any electrical device, and look at, you can't see this here, but look at the information on your charger and see if you can find the input and the output. So input means you can input usually 100 to 240 volts and 1.5 amps of alternating current. And you can see the little tilde sign means alternating current. And then look at output. So you have output on your device. And so that means like the computer charger will convert that voltage into, in this case, 9.5 volts. You can see here, this one actually, this has the symbol for direct current. And so most countries that use AC usually operate at about 50 to 60 hertz. So you can see that here, this is the input that it can take. So now, we know what can be input into our computer chargers or any electrical device. And we know what that charger, for example, will change the output voltage. So like I said, most countries use alternating current, like that's what comes out of the wall. So you can see here, the different wall outlets vary from country to country. So if you guys have traveled abroad, have lived abroad, or have even plans to move or travel abroad, you're going to want to know the differences between not only the different types of outlets, but also what is the voltage that's coming through in any different country. So in Europe, Australia, and New Zealand, those outlets actually output about twice the amount of voltage compared to American outlets. And so as you can see, most, it's a good thing most devices, double check, but most devices can take between 110 to 240 volts. And some devices you can switch between the two. But if you happen to have a device that only takes up to 120 volts, and it might say that on there, and you go to a country where 240 volts are coming out of the wall, that will be a problem. So I actually had this happen to me. When I moved to Australia, I looked, I knew the wall outlets are different, right? So I have my American plugs, and so I obviously needed a wall outlet to be able to plug in my American appliances. And that worked fine for my laptop, right? Because it could, I read on the label here that it could take 110 to 240 volts. But it didn't say anything on my nice Qi hair straightener. And so actually, I don't even know why I took a hair straightener. My hair is like naturally poker straight, either fortunately or unfortunately. So what happens is I get over there, I plug in my hair straightener, and it like burns out immediately. So you can see the difference here. I had to eventually get an Australian hair straightener, which had the correct outlet. But you can also see, I actually looked at the label this time and said that it can input 110 to 240 volts. So whether or not you're going to need a voltage converter depends on the voltage capacity of your electrical device. So check that out. And so generally speaking, if the voltage is too high, it's going to draw too much current and burn out. And so that's what happened to my American straightener, right? Because if I'm plugging in a 110 appliance into a 220 or 240 outlet, it'll heat up really fast and burn out in a matter of minutes. So that's what actually happened. But one way that I could have avoided that is to use what you see here. This is called a step-down transformer. And it's a type of transformer which converts a very high voltage, like you would have in Australia and New Zealand, on the primary side here, and it converts it into a low voltage at the secondary side. And so that would work out, right? If this is, you plug this into the wall, and so you have a high voltage coming in, and then you plug your, device that takes a lower voltage, like a hair straightener from America, into the outlet here. So now sometimes I think hair straighteners come with a dual voltage. So if you travel, get one of those. But that's actually why, you obviously don't want to be traveling with one of these step-down converters or transformers. But that's actually why we can use AC in our house. So we can get AC into our wall outlets, and how we can plug in most of our devices that use direct current. So we transport usually electricity from a power station, and it can go to like our towns, our houses, our businesses. And we use AC because it's easy to increase and decrease the voltage using a transformer. Just like we saw before, you could have one in your house if you've moved abroad. So like I said, most homes and offices are always AC. And the reason they do that is because generating and transporting AC across long distances is relatively easy. So at very high voltages, over 110 kilovolts, you lose less energy in electrical power transmission. So higher voltages mean lower currents, and lower currents mean less heat generated in the power line due to resistance. So AC can be converted to and from high voltages pretty easily using those transformers. And so where is a good application of AC and the relationship between AC and DC, not just in a band. So one thing I wanted to talk about was solar panels. So I don't know, maybe some of you have solar panels or have studied the way they work, but solar panels actually produce direct current, right? Because the sun stimulates the flow of electrons on the panel. So electrons, are moving around, and they actually flow in the same direction. So that's direct current, right? So how like I said, batteries use direct current, and they have a positive and negative terminal, and the current always flows in that same direction between those points. But like we just talked about, the US grid system and the power coming into your house uses AC. So if we have solar panels generating direct current, and we need to actually produce or be able to use electricity within our house, we need to convert that into alternating current to get on the grid or use it within your own home. So that's why you can see here, there's inverters that converts that DC into usable electricity. So you can actually get AC solar panels, and they have microinverters already integrated into the solar panel. And so I'm not sure, like I said, maybe you guys have homes with solar panels, or your parents, or somebody that utilizes that. And so how that relates to engineering, economy, and ethics is what we look at as a distributed energy resource and net metering. So basically, like I said in this previous slide, you can generate enough electricity to power your own home. But if you live in a very sunny place and somewhere that gets a lot of direct sunlight, you can produce more electricity than you actually utilize in your own home on a daily basis. And that would be, sold back, go back to the grid, and you can sell it back to your supplier. So what actually happens, more people are adopting rooftop solar panels. And that's good for engineers and economists, right? Because we're all looking for affordable, reliable, and environmentally responsible energy systems. And so in a distributed energy resource network, sometimes it becomes an issue of ownership and selling electricity back to the grid, back to that wholesale marker, and what they charge you to buy it back, or charge other people in your distributed energy resource network to buy that back. So that's something to think about. If you become part of this like engineering economy, is how do you develop affordable, reliable, and environmentally responsible energy systems um, that are beneficial to not only the people in the community, but that makes it affordable and available to everyone in these different communities so that you ultimately have cleaner energy. So I hope you learned a little bit about the conceptual ideas behind AC and some of its applications. And hopefully in your future work, you can move forward and applying these ideas.